Hi everybody, it's Mr. Spudik again, and today we're talking about projectile motion. So with projectile motion, the idea was this. Previously, you learned about something going purely horizontal. Then you learned about something going purely vertical. Well, what happens if you have, say, a ball flying through the air and it has both horizontal motion and vertical motion? Well, you should have already in the previous lesson learned about vectors and about vectors going in different directions and doing the math to break down those components. Okay, today we're going to just talk about those components. We're going to talk about how horizontal and vertical interact and how they don't interact. Okay, so let's begin. This picture here is of a ball flying through the air. It's going both up and down, okay, and horizontally left to right. All right, so this could be a ball flying through the air, could be whatever, something going through that air. And this is a way most objects will go through the air. Okay, now the red arrows show the actual velocities at certain points. Okay, so the magnitude and the direction of the actual true velocity. Then we have the black arrows, and black arrows show the horizontal and vertical components at each point. Okay, now notice something. You have the vertical arrows are going to be getting smaller as it moves along, okay? And the horizontal components are staying the same, all right? And that's what we're going to learn about today, okay? If you think about this picture as purely, let's pretend this was just a pop-up, and don't worry about the horizontal part. You have probably already seen a picture just like this, where you had a ball with a certain velocity going up, and then as gravity, right, we've talked about how gravity will continuously subtract 9.8, basically every second, you're subtracting 9.8 from that velocity, you're going to constantly be subtracting velocity. So notice that's what's happening with those vertical arrows, just like in a pop fly. Now horizontally, it's really boring. Okay, horizontally, notice how all of these arrows are the same length. All right, a couple other things. Notice at the peak. At the peak with a normal pop fly, just a purely vertical thing, you would have a vertical velocity of 0. And in this picture here, you still see that vertical velocity of 0. Okay? Which is why the red arrow is only going to be the horizontal velocity. It's the same length as the other black horizontal arrows, but that's the true velocity at that peak is just going to be the horizontal velocity. Okay? All right. Now, you see, as I mentioned already, the components. I want you to realize that these components are completely independent of each other. Okay? Meaning, it does not matter how fast something's going horizontally. Gravity is still going to subtract away from the vertical. Okay? It doesn't matter how fast something's going vertically. Horizontally, that's not going to affect how that horizontal motion goes across. Okay, so what I'll say a lot is vertical has nothing to do with horizontal. Horizontal has nothing to do with vertical. It's almost as if you could take this picture of one ball going through the air vertically and horizontally, and it would be the same thing as if you took that one ball and you had just a vertical pop fly and just a ball that's moving along horizontally with no acceleration. Okay, so vertical has nothing to do with horizontal. Horizontal has nothing to do with vertical. They are completely independent of each other. All right, now notice this. We have tennis ball A and tennis ball B. Okay, and tennis ball A is going to be dropped from a height. Tennis ball B will be from that same height, but was given a horizontal initial velocity. Okay, you could think of it as one ball was being dropped, ball A was being dropped, and ball B is going to be rolled across the table and is going to leave the table at the same instant and the same height that ball A was being dropped. Okay? Well, let's look at the horizontal piece first. Notice the spacing for ball B. After every second, that spacing is the same. And that's because horizontally, there will be no acceleration. There will never be an acceleration horizontally for that ball. Okay? Now, vertically, notice that ball A and ball B, they both are going to be spaced and the spaces are going to get further and further apart. You know this already because of gravity, right? gravity is going to have that ball speed up as it's falling, okay? But I also want you to notice that ball A and ball B are always falling with the same distance and the same spacing. Okay, so no matter what, no matter how fast ball B is going horizontally, it would never affect how it fell vertically. And it would be vertically just like ball A that was being dropped. Okay, always, no matter what, no matter how fast ball B goes horizontally, vertically it will fall just like ball A. Okay, and that might go against your thought. It might be something that you say, no, well, what if it's really, really fast? No, it will always fall at the same rate as ball A. All right. Here's a beautiful picture of me diving somewhere. I'm just kidding. It's not me diving. But I want to show you something here, okay? In this picture, what type of path do you see that diver doing? Okay? Think about a mathematical path. Something you've learned in algebra or geometry. What would be the word of the path that you see here? Did you guess parabola? That's what it is, okay? And so with projectile motions, everything will be moving in a parabola. Now, there'll be two types of problems we cover in projectile motion. First half, and usually what we start with are easier ones where you just see half a parabola, okay? Think of that ball rolling off the table again, okay? If the ball is rolling off the table, okay, you would just have this half of a parabola like you see here, all right? That will be one type of problem. Later on, we will deal with problems that go up and back down, like I showed you in that first picture of the ball going up and back down. But usually it's easier to break things down into just a half parabola type of problem. And what we would say is those are problems where you do not have any initial vertical velocity, okay? So you're not jumping up, you're not jumping down, you're going to go horizontal, just like a ball rolling off a table, okay? All right, let's just talk about the components quickly. For our horizontal components, the acceleration will always, always, always be zero. Gravity does not affect the horizontal motion. Gravity only pulls down, okay? So you will never, ever have acceleration horizontally. It's not like there's a rocket that's going to be strapped to the ball and make it accelerate that way, okay? So when a ball is just flying through the air, there's no horizontal acceleration, only vertical. All right? Now, if you want to think about the equations, all right, the equation we've used before, that makes a lot of your equations. You know, I only give 3 equations, okay? And honestly, only one, this equation right here, which I call the big ugly, that's the only equation that would be useful. Because the other 2 equations, if you cross out acceleration and make acceleration 0, you don't have a formula anymore. Okay, and even this equation, the acceleration, the 1/2 at squared, that whole thing's going to go away because the acceleration is 0. So you have a very boring problem. It's just a problem with 0 acceleration, which is what you probably did at the very beginning of the year. Okay? All right, remember, velocity will never change because the acceleration is always 0 horizontally. Now, vertically, we have gravity. All right? We have gravity, negative 9.8 meters per second squared. So that will always be pulling down, okay? On occasion, many times we'll be using still that big ugly, okay? And especially when we start out, I'm going to have those half parabola types of problems where the initial velocity often will be 0. It's not like the velocity is going to be starting up or starting down. So most velocity or most problems when we start those half parabola, okay, initial vertical velocity of 0 problems, it'll just be horizontal, which means this equation will be used a lot where the initial position and the initial velocity are crossed out. And you'll be getting so much practice solving for time. I even put the equation there again, where if you had to solve for t in this equation, you'd have t is equal to the square root of 2xf over a. Okay, you can check your math on that later, but you will be seeing that a lot when we do these half parabola problems. Okay, and just remember, velocity is always changing, always have that negative 9.8 meters per second squared. Okay, So I'm a baseball fan. I'm a big Nationals fan. And I always wondered, because I'm not a big baseball player. I didn't play that much baseball, okay? And I always wondered, when I started watching it a lot, why is a changeup such an effective pitch? I mean, you're just throwing it slower. What's the big deal of that? Okay? I mean, if you're throwing a fastball, that's really hard to hit, right? But a changeup is just slower. Isn't it easier? And obviously that means I didn't know much about baseball, okay? But just to explain to you, two reasons we can talk about in physics, okay? The first one would just be timing, okay? If you think about the horizontal distances traveling from the mound to the catcher, okay? If you have a much faster ball, you have a fastball, and you're throwing it, say, 95 miles an hour, all right? Well, that batter is really having to get ready, and he's timing exactly when he has to swing. If all of a sudden you're throwing a ball that's 85 miles an hour, his timing will be off because he has to start his swing for a fastball, and when the changeup comes, he's already gone through his swing when the ball comes by. Okay, so that's just timing, and that would be distance over time, basic old velocity that we covered at the beginning of the year. But the reason I bring this up is you can also think about the parabola. Okay, no matter what, when a ball flies through the air, it's going to be in a parabola. However, if you have a much higher horizontal velocity, that parabola is going to be much further stretched out. All right? Where if you have a changeup, that changeup is going to have a shortened parabola from his hand. And so that ball is going to drop lower and below where you think it's going to be. So when you see Daniel hits Murphy here, who was an excellent hitter for the Nats a while back, all right? Daniel hits Murphy, if he's expecting to hit a fastball, okay, at a certain point, and it's a changeup, well, then that changeup, that ball will be below where he's expecting it. Okay? All right. Ladies and gentlemen, thanks for watching. I will see you next time.